We are in chapter 5 once again, and we will be examining the Thevenin Norton equivalent circuits. So let's go in detail now. This equivalency a bit different from the previous ones, and we will see in details what are those differences. Thevenin equivalent, let's start what it is first. So we will be examining the Thevenin equivalent, this frame as a video, and another frame, another video. This frame video includes the calculation of the Thevenin equivalent circuits parameters, and this is what it is and what information do we need to understand the Thevenin equivalent circuit. So come to the first frame, Thevenin and Norton equivalence. A linear circuit which includes two or more elements has an equivalent circuit called Thevenin equivalent, which is combined of an independent voltage source in serial with a resistor. Now here you are what I am saying. See in this frame as well. So we've got a linear circuit. This is a linear circuit which includes two or more elements. There are many elements in it, and this circuit is going to be replaced with these two elements. These elements are connected in serial. One of them is independent source, the other one is a resistor. So all the elements in here with their topology is going to be transferred to this circuit. This circuit is called Thevenin equivalent circuit. So the source transformed form of it is the Norton equivalent circuit, which is combination of an independent current source in parallel with a resistor. So if you come here, we use the equivalency now. So we've got a linear circuit which has got many elements in it, and the output of this element could be another circuit or could be just one element in here. If it is just one element in here, it's going to be the output element. If it is a circuit here, that is the cascade circuit which is connected to the linear circuit A here. What we are saying is this: if the linear circuit equivalence is this, which is the Thevenin equivalent, then all the currents and voltages in this common circuit will be the same. That means if you replace that linear circuit A with this Thevenin equivalent circuit A, then common circuit elements, currents and voltages are going to be the same. That's why we call it equivalent. So what happens is this, quite interesting. So there is a circuit here which has got many elements in it and has got a topology. So you are replacing all these elements with just two elements in serial with each other. So just two elements mean one of them is independent voltage source, the other one is a resistor. So independent voltage source voltage is called Thevenin voltage. This resistor is called resistor. Now we are going to see the next step. Once a linear circuit A is given to you, how you are going to find the Thevenin equivalent circuit to this circuit is the next question. In order to find that, we've got to remind you some of the concepts that we are going to use. These are related with short circuit and open circuit concepts. So we're going to use these concepts while calculating VTH and RTH elements of the Thevenin equivalent circuit. Here we are. There is a given circuit here. This given circuit has got 5 elements in it. 5 elements in it, yes. Now, deactivation is a new concept. Deactivation of the dependent and independent voltage sources means voltages become zero. When you say I deactivated an independent source, that means you change this independent source voltage from a known one to zero. That's short circuit. Practical meaning of this making the voltage zero is that remove these elements and connect it to terminals with a wire. This is what is done here. So here you are, there is an independent voltage source here. When we are deactivating these independent sources, we are removing these independent sources and put a wire in between the terminals of these independent sources. So what happens is this: the voltage of this, the voltage difference between those two terminals is going to be the zero, that's short circuit, but there's going to be a current passing through this wire, which is also the same current of this resistor. So when you make the short circuit, it doesn't mean that the current itself, the current also is zero. The current, it could be any value, you can calculate that. So there is a short circuit current, but short circuit means voltage is zero. So deactivation of the mains is the power source at home. Deactivation of this is dangerous, we are saying. Deactivation means you're going to make the voltage of these elements to zero. You're going to put a wire between two terminals. When you put that wire between the terminals, that means you are forcing 220 volts independent source voltage to make it zero. So there's going to be a high current passing through to your body, So that is very dangerous, don't do it. It says here, if lucky, fuse blows before you die, that is. So be careful, don't do this. And if somebody else does it, stop him or her from doing that. So in here, deactivating independent voltage source, as a result, we can say, conclusion, when we deactivated independent voltage source, we are making the voltages of this element zero, means connected a wire here, short circuit, the current is I, it's going to be. Let's come to the open circuit business. If there is no device connected to mains, that it is open circuit. So at home, you got a source, independent voltage source. If nothing connected to it, it is open circuit. So that means there is no current go anywhere, and there is no current passing through this independent source. So current is zero. If the current is zero, the voltage is known, that is independent voltage source voltage is known. Current times voltage, since the current is zero, it's going to be zero, that means power is zero. So that means if your independent voltage source at home is open circuit, there is no power delivered. So that means it is deactivated when the current is zero. That's full point. So deactivation of the independent current or dependent current sources. So what we said here is going to be repeated. So independent voltage source made the voltage zero, short circuit. Independent current source made the current zero, that is open circuit. Practical meaning, remove the element's terminals on air. There is no open circuit voltage between these terminals. Here you are. So if you want to make this, assume that this is an independent current source. When you make it open circuit, you're going to take this wire off that means no current passing through. Then it is open circuit. So you've got to assume this current source, that is, not the voltage source but current source. Then the current is zero, open circuit. So current is zero, but there is a voltage between those two terminals. So there could be a open circuit voltage. If there is a resistor, so let's come to the open and short business for the resistor elements. If a resistor is short circuited, then VR equal to zero. Short circuited, voltage is zero. But if it is a resistor element, when you make the voltage equal to zero, due to the definition relation, the current is going to be zero as well. Why? Because the R is a positive real number. If VR is equal to zero, then IR equal to zero. The result is, if a resistor short circuited, it is also open circuited. So how are you going to do what we are going to do in practice related to that activation? All you've got to do, remove the resistor from its terminals. For example, you could see it in the example. When you short circuited here, A and B, we are going to put a wire between those two. That means you short circuited this 3K resistor. So this is what you have done. Once you have done this, 3K resistor voltage is short circuited, then the current is zero, then we've got to remove it, so it has been removed here. So I have removed this resistor from its terminals and put a wire between A and B, make the voltage equal to zero. So that means now the resistor's terminals, the voltage between the resistor terminals is going to be zero. And there is no current passing through the resistor. I removed it. This is what happens to the resistor when you make it short circuit or open circuit. So you're going to take this out. So remember that we have removed the resistor. The reason is this: remove the resistor means current equal to zero. That means open circuit. But if you don't remove it, if you put a wire there, there is going to be a current passing through, so you cannot say it is open circuited. Therefore, whether it is open circuit or short circuit, resistor should be removed from the circuit. In practice, what happens in this example, if you say that A and B terminals for a given circuit, so go back to our given circuit here. If it says that A and B terminals should be short circuited, this is what is done here. Then I could do step by step, many actions comes in. If this voltage is zero, that means the resistor voltage is zero. That means the resistor is open circuit at the same time. That's why I removed the resistor. So there is no resistor you could see here. Since this voltage is zero, A, B terminals short circuited, voltage is zero. That means that V is zero. But there is a dependent source here, of which voltage depends on the voltage between A and B. I already made this voltage equal to zero. Therefore, this independent voltage source voltage is zero as well. So I put this short circuit here, make a short circuit. So if somebody says that I and B terminals is going to be short circuit, there are three actions happened here. You put a wire between the terminals A and B, you remove this resistor, and then you have short circuited this dependent voltage source here, because the voltage of this element became zero due to the short circuit of A and B. So that means there are many actions happening at the same time if you do one short circuit or open circuit somewhere in your circuit. So you've got to pay attention if this happens. So this is the end of this video. So in the next one, let's see what we're going to see next. So in here we explained Thevenin equivalent circuit and some information that we're going to use later on. The next video is going to be about how we are going to calculate Thevenin voltage and Thevenin resistance calculations, how we're going to do this. So that's going to be the next video.